We covered pretty much everything that I want to cover about mass spec yesterday, which is not a lot because you're not going to see it often, and the ways that you might see it would ask you a question like, which of the following is a molecular ion for the compound above? Or which of the following is not a molecular ion? Or looking at the mass spectrum below, which signal is the base peak? So I'd like you guys to quickly look at the mass spectra that I have. First of all, can you identify the mass spectra? Can you distinguish which of those on there are the mass spectra? Look at the mass spectra and tell me what is the base peak for the mass spectrum on the left? What is the base peak for the mass spectrum on the right? Jaylee? For the one on the left? 72 is not the base peak. Should we do a quick review on what the base peak is? Definition? Most abundant? Because actually the signal is created by fragments or ions of that mass hitting the detector. So the more fragments that hit the detector at that mass, the larger the signal. So the most abundant signal is our base peak. Does that change your answer, Jaylee? There's really only two labeled, right? So if it's not one, it's the other. So what might we suspect 72 is then? Obviously, it's not the base peak because just by definition, 43 is the base peak. 43 maybe represents the most stable fragment. But 72, do you think that tells us anything about our spectrum? Or our compound, I mean.
Isn't that the weight of the compound?
Our molecular ion signal. Yeah. Typically, the highest mass signal is the molecular ion signal. And I say typically because it's never that easy. There are isotopic clusters that show up in mass spec. For instance, if you have bromine or chlorine, bromine's a really good example because bromine is 51% bromine 79 and 49% bromine 81. Which means if you have a fragment containing bromine, 50% of the time that fragment is 2 mass units heavier than the other 50% of the time. So when the molecular ion forms and bromine is involved, 50% of the time you get a molecular ion, and 50% of the time you get the molecular ion plus 2, rather than molecular ion plus, M plus for the molecular ion. It's the molecular ion plus 2 mass units. So typically the heaviest signal is the molecular ion, but isotopic clusters can actually deviate that. The other thing is, the other reason I say usually, is because sometimes the molecular ion is not stable enough to make it to the detector. So first of all, you see this little peak at 73. That might be an isotopic cluster because of carbon-13 that's in the structure and deuterium, H2, that's in the structure, adding just small amounts of mass every now and again. But what if 72 is just a heavy fragment and the molecular ion never actually formed? We can't rule that out. Which is a challenge when you're solving mass spec. The thing is, you're not going to have to solve mass spec in this class. That's like a spectroscopy course endeavor.
So this is like not related at all.
Tell me.
But I just have one question on the nomenclature.
Oh, yeah. Oh, we said we'd start with that, but I was just so excited for spectroscopy. Tell me.
For the last one,
Yeah?
I'm just confused why you use the liquid signal. Like, why would it not be?
Oh, did you see above it says check that the name is correct?
No,
Ah,
That's
right.
where we're going.
There you go. Well, I'm glad you caught that. Okay, we'll talk about that one. Okay, I want to say this because it's not something I talk about in the OCHEM 1 series, but it is kind of a cool feature of mass spec. If you take what you know to be the molecular ion and you divide it by 12, you can often guess at how many carbons are in the structure. Now, I'm going to not divide by 12 yet because I know for a fact that this molecule has at least 2 oxygens. I'm only saying that because or at least 1 oxygen. I'm saying that because up above I gave the chemical formulas. If I divided this by 12, I think that's 6. And there's no chemical formula that is C6. That's not an organic molecule. So there's something that's contributing here. So I'm going to take out the mass of at least 1 oxygen first, which brings me to 56 mass units. If I divide this by 12, it can give me an estimation of how many carbons are in my structure. It's going to be 4 and something, right? 4. It doesn't really matter what the decimal place is because all of that extra mass probably just comes from hydrogens. So this is a chemical formula that probably has C4H something and O. And I got a little bit lucky by just subtracting 1 mass of oxygen. But there's ways to decipher some of that information to tell you more about your chemical formula. So because we know the chemical formulas, one was C4H8O, the other was C8H8O, 2. I'm going to say that we're probably looking at the smaller mass, the smaller chemical formula, C4H8O, when we look at the left. Okay, the mass spectrum on the right, which signal is the base peak? 91's the base peak. And there are correlations that you can make between the masses of these fragments and the structure of the ion that's coming up, but it's not going to be something you do very often in this class. So rather than taking a lot of time to go through it, I'm just going to say 91 often represents a benzyl unit, which is an aromatic ring with a carbon coming off of it. So the molecular or the mass spectrum for the structure on the right is suggesting that there's an aromatic ring. And we will look at the other spectroscopy, the other spectra, to try and confirm that, to try and prove that there really is an ion in the ring. You're right. I wanted to do some spectroscopy. If I pause the camera, are you guys brave enough to come up to the board and solve some of the problems? Did you work on them between classes? No? Yes? Okay, then how about this? We'll go through them together, and you guys don't have to come to the board if you don't want to. But if there's one you want to claim, you're welcome to come up and name it or draw it. So let's review some of our rules for nomenclature. First, we want to find the longest carbon chain, correct? But there's a little bit more to it than just the longest carbon chain. We want to find the longest carbon chain that contains our highest priority functional group. So what's our highest priority functional groups? We prioritize functional groups from OCHEM 1. Alcohols, alkenes and alkynes, tied. And then alkyl and halo groups. If there's no alcohol, then the highest priority we search for is the alkene or alkyne. If there's both an alkene and an alkyne, then we try to find the longest carbon chain that has both of them. We maximize the carbon chain with both. If there's no alkene, alkyne, no alcohol, then we just look for the longest carbon chain that has the most substituents. We want to have the most groups coming off of it. So structure number 1, no alcohol, no alkene, alkyne. So I'm just looking for the longest carbon chain. No matter what I do, that's going to be a 5-carbon chain. And the suffix, we did talk about the suffix yesterday, right? The suffix won't be impacted by alkene or alkyne, won't be impacted by alcohol. So the root and suffix together for this compound, ignoring the prefix, becomes what? Pentane. This is a pentane derivative. Now, should I number from the left to the right, or from the right to the left? Right to left? If we number from left to right, we get a locant set of 2, 2, 4. I have a methyl group at 2, a methyl group at 2, a chlorine at 4. If I number from right to left, I get a locant set of 2, 4, 4. Sounds familiar, right? The idea of numbering both directions to find different locant sets. Which of these is a lower locant set? Why is the first one lower? They both start with 2. It's lower at the first point of difference, and that's what we're going for. It's not just the lowest locant set, it's the lowest locant set at the first point of difference. So I want to number this with my red locant set from left to right. That's because alkyl groups and halogens have no distinction between them. So the reason that I number from left to right is not to give the lowest locant to the alkyl groups or the halogens. It's just to get the lowest total locant set. They're of equal priority. When I put these into the name, I alphabetize them regardless of their locants. So I'm going to have 2 methyls. That's going to go in as dimethyl. And I'll have chloro. What of those groups should I put first? Because C comes before M. We don't alphabetize the dimethyl by D because the multipliers aren't our group. So 4-chloro, 2,2-dimethyl pentane. I ran out of space. Sorry. You guys know how to spell methyl, right? Is it too redundant to have to say 2 twice? Couldn't I have just said 4-chloro, 2-dimethyl? What if I'm not sure that you forgot a locant? Because there are structural isomers that could be here. This could be 2,2-dimethyl. It could be 2,3-dimethyl. So I really want to make sure that you told me the right structural isomer. If you have 3 substituents, 2 methyls and a chloro, you should have 3 locants, 2, 2, and 4. The number of substituents has to agree with the number of locants, even if they're repeated locants for the same group. All right, the structure on the right. What is my parent chain? Prefix and root. Or I'm sorry, root and suffix. The parent chain. Cyclohexane. That's my longest carbon chain. And it has 3 substituents coming off of it. Is it obvious that our numbering here is going to start on one of the carbons that has a substituent? I could start anywhere. Makes no sense. And I'm going to start on one of the 2 end substituents and number the other direction, just because that will always give me a locant set of 1, 2, 3 or 1, 2, 3. So I don't need to go through and show you that our locant sets are tied. 1, 2, 3 from left to right, 1, 2, 3 from right to left. So if I have 2 locant sets that are exactly the same, I get to just pick whichever one I want. Or what's the rule? A tie goes to the alphabetical substituent. If I have two locant sets that are of equal value, then I choose the one that gives the lower locant to the first alphabetically. So what's the first alphabetically? What are these groups? Bromo. What about this middle group? Isopropyl. And this group on the right? This is isobutyl. We could also name isopropyl and isobutyl using substituent names. So isopropyl can be called methyl ethyl. It's a 2-carbon chain with a 1-carbon substituent. It's an ethyl substituent that has methyl coming off of it. It's not just ethyl, it's a methyl ethyl. And isobutyl could be called 2-methylpropyl. And because these substituents have descriptors inside themselves and locants inside themselves, they get put in parentheses so that their locant goes in front of the parentheses and describes everything. If you decide to do this, the way that you name them changes a bit. Isobutyl is alphabetized by I, but 2-methylpropyl is alphabetized by M. So it could change the way that it shows up in the name. I'm going to use isopropyl and isobutyl. But that tells me that bromine comes first alphabetically. Out of these 3 substituents, bromine is the first alphabetically. So I'm going to number this from left to right. What comes next? Isobutyl or isopropyl? Yeah, B comes before P, given that iso is the same. So our full name here becomes 1-bromo, 3-isobutyl, 2-isopropyl, cyclohexane. I love how the name is mostly prefix. We're just taking so much time and space to write out the substituents on the group. All right, now to some more fun compounds. Here I have both an alkene and an alcohol. So what's the best way to number this structure on the bottom left? Jew? Top to left?
Oh, sorry, I was looking at the wrong one.
You were looking here. I see. Yeah. Well, we can do this one if you want.
No, we can go, so that one would be right to left.
Right to left. Because it's obvious that the alcohol is going to get its lowest locant moving from right to left. And I care only about the alcohol right now, since the alcohol is my highest priority group. I want it to get its lowest locant. All right, the alcohol is going to show up in the suffix, which means I need a locant in the suffix to tell me where the alcohol is. But the alkene also shows up in the suffix. So it's useful if I split my suffix into locant, ene, locant, all, to be very specific about where everything is. So in the prefix, I have a methyl group at 3-methyl. And then my parent chain is 6 carbons, so that's hex, 4-ene, 2-all. 3-methyl, hex, 4-ene, 3-all. There is another way that you could write this. You could take the first locant of the suffix and put it in front of the root. But you can't take both locants of the suffix. The 2-all is going to have to stay exactly where it is. But we could write this as 3-methyl, 4-hexene, 2-all. Some people like that more. Some people don't like that more. IUPAC says that the one on top is the best way because it's the most specific about where everything is. I think that's fair. All right, Drew, you already got us started on the next one. How should we number?
Top to
Now you're saying top, but could you be more specific?
for alcohol.
Start at the alcohol's carbon and move to the alkene carbon. You guys agree that if it's in a ring and I get to start anywhere, I'm going to start where the alcohol is? And if I can move either direction, but the alcohol already has its lowest locant set, now I'm looking to prioritize my next highest priority group. I want to get the alkene its next lowest locant, since the alcohol already got its. That wasn't something that I could satisfy in a linear chain, but it is something that I can take advantage of in this cyclic chain. What's the name of this group coming off of this? The alkyl group? Tert-butyl. And tert-butyl is different than isobutyl. The tert, I'm not good with my handwriting. The tert is italicized. The tert is a descriptive term for butyl. The tert is not part of the alphabetical name. So this is not alphabetized by T, it's alphabetized by B. And if you wanted to give a systematic name for tert-butyl, this is again a 2-carbon chain, but off of carbon 1 are 2 methyl groups. So this is 1,1-dimethyl ethyl, if you don't want to call it tert-butyl. And how would you alphabetize dimethyl ethyl? D. The weirdest thing, you don't alphabetize by multipliers unless they're inside of a substituent name. In that parentheses, you just pick the first letter. It's like you're not even reading what it is. I don't know who came up with these rules, but they like nailed some of them on the head, missed some of them, ran right into the door. Okay, so I'm going to call it tert-butyl if you guys are okay with that. And because I aimed to minimize the locant for the alcohol and the alkene, tert-butyl ends up on position 5. 5 tert-butyl cyclopent 2-ene all. Do I need to say that the alcohol is at position 1? Does it hurt if I say 2-ene 1 all? Definitely doesn't hurt. But because this is a ring, and because the alcohol is my highest priority, and because I get to start wherever I want to in a ring, I'm starting where the alcohol is. So of course the alcohol is at position 1. But it's not wrong if you wanted to throw that in and say it. 2-ene 1 all. Fun, right? Okay, I know something I missed, and I always miss this. I don't know why. It's just like my tendency to miss it. The last alkene that we did had a trans-cis isomer, and we didn't name whether it was trans or cis. So we should put in the front of this compound trans or cis. Trans. This compound doesn't have trans-cis isomerism. Despite being a trans alkene or a cis alkene, it doesn't have a trans isomer. Do you guys see what I'm saying? It is a cis alkene, but there is no way that it can be trans and still be part of a 5-membered ring. So we don't describe the alkenes in rings as cis or trans until that ring is 8 carbons long or longer. Then those long chains can have trans alkenes. Here, it's only cis, so I'm just going to leave it at that. Down here, again, I have a trans alkene. The bromines are actually the high priority groups, and the bromines are trans to each other. But now the question is, should I number this last compound from right to left or left to right? Pamela? Right. Esmeralda? Sorry. I'm sorry. You guys shouldn't have sat next to each other and wore scrubs all the time. That's my fault. Right to left? Tell me why. Well, the alkene is of equal priority, so why not minimize the locant for the alkene? What do you think? if I prioritize the locant for the alkyne, the locant is 1. Can't get any lower than 1. If I prioritize the locant for the alkene, the locant is 2. Which of those is a lower locant set for the equal priority groups? 1. So I'm not ignoring the alkene. I'm not saying the alkyne is higher priority. I'm actually looking at both of them. And since the alkene and the alkyne are of equal priority, I'll choose the numbering that gives either one of them the lowest possible locant set. What would happen if they were tied? For example, if this were one carbon short in the chain, the alkene starts at position 1, the alkyne starts at position 1. It's a tied locant set for my tied priority groups. A tie goes alphabetically. Tie goes to the first alphabetical. So what comes first alphabetically? Alkene or alkyne? Alkene. So the alkene is only ever higher priority than the alkyne if there's a tie for both groups. If there's not a tie for both groups, either one of them gets the lowest locant set. That's the rule. Great. So trans something. I'm starting with orange because it gives my alkyne position 1. So that means I've got 3,4-dibromo. My carbon chain is 5 carbons long, so my root becomes pent. And in the suffix, I have 2 suffixes. I have an alkene that starts at position 3, and I have an alkyne that starts at position 1. Trans 3,4-dibromo, pent 3-ene 1-ine.
Sorry, to go back to what you were saying, if you had a tie and the locant set for the first priority, but like then it would, how do I say this? The locant set at first kind of difference if you're lower for beta, obviously. You know what I'm saying? Like let's say bromo, we're basing it, you don't base it off that at all. Like the lowest locant set.
No, you're right.
You get what I'm saying?
Yes, I'm not looking at the total lowest locant set for all substituents. In red, my locant set would be 2, 2, 3, and 4. Do you agree? Mm-hmm. That's the alkene, the bromine, and the alkyne. In orange, my locant set is 1, 3, 4, oh no, 3 and 4. But actually, orange is still a lowest locant set.
Well, I was saying, sorry, if you took away, when you were saying like the alkene and alkyne are both at 1.
Oh, right. Okay, so
If it was like that. Which still, it would still go that way because of, even if you were doing it alphabetically or.
correct. It would still go from this direction because of the alkene being tied with the alkyne and the alkene being first alphabetical, not because of the total lowest locant set.
So you just ignored that.
We only look for the total lowest locant set when all of the things are of equal priority. We could have made a lower locant set for this. I think this is a good example. If I had started at the tert-butyl, I could have numbered 1, 2, 3. I could have gotten my locant set to be 1, 2, 3. But because I have to prioritize the alcohol getting its lowest locant set, then prioritize the alkene getting its lowest locant set, the tert-butyl ended up on 5 instead of having a locant set that ended at 3. So we could have had a locant set of 1, 2, 3, but instead we had a locant set of 1, 2, 5, and that's what we went with. That's not the total lowest locant set. That's just the total lowest locant set for the alcohol and then the alkene. Yeah, crazy, right? The priorities make a big deal. A big difference, I mean. Okay, now we draw them. Esmeralda.
Sorry, why is there 2 2s in the first column, like methyl dimethyl? The very first column. The
Uh-huh.
chloro 2 dimethyl. Yeah.
Why are there 2 2s?
Yeah.
because there's two methyls, and they're both on carbon 2.
Oh, okay.
If one of them was on carbon 3, I would have said 2,3-dimethyl, but one of them's not on carbon 3, and I want to be very specific about where both of them are.
So if we put like 2,2-methyl, would that technically be correct? Or does it
No.
have to put dimethyl?
Yeah, if you said 2,2-methyl, why did you say the methyl is on carbon 2 twice? You're not telling me that you have two methyls. To tell me that you have two methyls, you say dimethyl. That'd be like down here saying trans 3,4-bromo. One bromine at positions 3 and 4. Why would I have one bromine at two different positions? We add that multiplier to be as specific as possible. It is a little redundant, and that's okay. 3,4-dibromo, 2,2-dimethyl. That multiplies your question, right? Multipliers to say how many of a specific substituent, and locants for all of them. You guys know about forever chemicals, these polyfluoro hydrocarbon chains? Well, they're not really hydrocarbons, are they? If you were to give an IUPAC name for this, woof, I should have picked a smaller compound. 3, 5, 7, 9, 11, 14 fluorines. Oh, I don't know the multiplier for 14. Dectetra or something. I feel like they always combine 10 and a number. Tetradeca. But that sounds like 40. Tetradecafluoro. We'd have to name it 1112233445566 tetradecafluorohexane. Although I think at that point people would get the message. Polyfluoro. All right, for drawing them, you guys have drawn molecules. You got here by taking OChem 1, so I know that you've drawn molecules by name. Do you think about that process? Do you have a system for drawing a molecule by its name? Or do you just kind of wing it every time? You're not quite sure what you do to get there. Wing it. I start by drawing the root first. I draw the parent chain. And not even the suffix. I just draw how many carbons and whether it's a ring or a chain. Then I look at the suffix, because the suffix typically has those higher priority groups. So I'm just going to put those in first, because that will be landmarkers for me. So with our first one on the top left, 2,3-dichloro, 4-cyclopropopentane, I'm drawing pentane, 5-carbon chain. I can number this either direction that I want to, so long as I'm consistent about it. Okay, so 2,3-dichloro, here's 1, 2, 3-dichloro, 4 is cyclopropyl, which is such a fun little group, that little triangle. Now, the question is the name correct? Has it been named correctly? In my OChem 1 classes, I love to give a molecule that is named incorrectly, have students draw it by the name, because it's still possible to draw a molecule based on its wrong name. It just breaks one of the rules. And then they correct the name and they say what was wrong about it. And inevitably, I always have somebody that says, this looks great. That name's not wrong. That was not a trick question. Like, this is a trick question in a way. I'm asking you to prove that the name is right. But if I ever do that on an exam, please don't think that I'm tricking you and giving you an accurate name and asking you to identify that. I'm not. I want you to know the rules. And the rules are longest parent chain for the highest priority functional group, lowest locant set for the highest priority functional groups, substituents alphabetized. Those are pretty much the 3 rules. Okay, so is this the best name for it? Well, I would say the only other way to name this would be going from left to right, because it's already been numbered from right to left, 2,3-dichloro, 4-cyclopropyl. So I should just check that the other direction is not better. But I get 2, 3, 4. I get the same locant set, 2, 3, 4. The difference is the alphabetical position of the substituents, cyclo versus chloro. Which of those comes first alphabetically? Chloro. Yeah, H comes before Y. So because I have two locant sets that are tied, tie goes to the first alphabetically, which is going to be chloro. So it is named correctly because of the tied locant sets going first alphabetically. Okay, second one, 3-sec-butyl cyclohexene. Well, cyclohexene, I'll start with my cyclohexane. I don't really know where that alkene is. That's not true. I know exactly where that alkene is. Anywhere that I want it to be, because it's a ring, and the alkene is the highest priority group, so wherever I put it, that's position 1. Remember the rule about alkenes. We have to number through an alkene. We can't just start at 1 carbon and in the alkene and then move away from the alkene. We number through an alkene. So for this one, sec-butyl comes off of position 3. 1, 2, here's position 3. Sec-butyl is one, I don't know about your OChem 1 professors, but I don't talk about this as much. Much like tert-butyl says it's a 4-carbon system connected at that tertiary point. Sec-butyl is a 4-carbon system, but it's connected at this secondary point. Do you know what? I want to take a quick second to talk about those terms. Have we talked about them? Primary, secondary, tertiary, and quaternary. I think we did talk about them. They describe bonds to other carbons. And tert-butyl is meant to say 4 carbons connected at a tertiary carbon, which means a carbon that has 3 bonds to carbon. Does that carbon have 3 bonds to carbon? Is that a tertiary carbon? Is that not a quaternary carbon? So why do we call tert-butyl tert if it's quaternary? Is that not a tertiary carbon that we're calling a secondary butyl attachment? I think the reason that these get their names is because if you just say R, maybe R is OH, maybe R is Cl, maybe R is whatever, that's a secondary carbon. Same thing here, that's a tertiary carbon. So it is the substituent itself that we're describing as the tert-butyl or the sec-butyl, not necessarily the carbon in the context of the molecule that we're calling a tertiary carbon or quaternary carbon. Don't you just love that? It's so easy to teach in OChem 1, to tell students these are our degrees of substitutions and they don't apply when we look at them in these molecules. Love it. All right, here's our sec-butyl. Is this a good name for it? Could there have been a better name? A lower locant set? Anything? No. No better name. Now, I actually thought about giving, you know what? I originally had these named wrong because I wanted you to check them. I forgot that I had done that, so I changed this name. What it originally was given to you as was 2-sec-butyl cyclohexene. And so it would have looked more like this, 1,2-sec-butyl. Is there a better name for that?
Isn't it 1, the lowest level can't be 1, 1, not 1, 2.
Right. If I had a structure like this and I called it 2-sec-butyl, that just means I'm counting through the alkene and then saying that the sec-butyl comes off of the second carbon in the alkene. I can number an alkene in either direction. So I could have called this position 1 and this position 2. Either way, I have the same locant set for the alkene. The alkene is where I'm starting my numbering. but I can get a lower locant set for the sec-butyl, and I can just call it 1-sec-butyl cyclohexene. All right, the last one, and this is the one that Jordan was asking about, which makes me think you're not happy with its name, so I'm going to have you correct it. Start with the cyclopent, got a 5-membered ring. It says a alkene at position 2 and a 1,5 diol, so I'm going to put 1 for my alcohol. Here's position 2 for my alkene, 3, 4, 5 for my second alcohol. What are you not happy about with this one, Jordan?
It doesn't prioritize alcohol.
The alcohol has not been prioritized. Well, I mean, in a way, it prioritized one alcohol, but it did not prioritize the other. How would you have numbered it instead?
Right, left, like over the top, so alcohol,
Alcohol, alkene. Would you agree that I could have numbered this through the 2 alcohols and gotten a locant set of 1, 2, 4? Or started with the 2 alcohols and gotten a locant set of 1, 2, 3? I can prioritize my 2 alcohols in 2 different ways. I can get them both to be 1, 2. Then I'm just looking to prioritize my alkene after that. Great. So the new name, do you want to read it off for me?
cyclopent 3-ene 1,2 diol.
3-ene 1,2 diol. Great. And I might have messed up. I think that ene is supposed to have an E at the end of it because the multiplier diol, that multiplier di often puts the E back in that gets taken out. So that might be a little mistake. I won't take off points for you on that on an exam if you don't take off points for me on my rate my professor for that. Love it? Hate it? It's usually a love-hate relationship with nomenclature. I've yet to find anybody that's like, yeah, it's okay. Not the worst, but there's more interesting things. People usually love it or hate it. I love it. I hate to love it, but I do love it. So practice with it. We'll be using nomenclature a lot this semester. A lot of the final exam has questions where molecules are written in their IUPAC name, not drawn out. So I want you to be familiar with interpreting both directions. Okay. I want to go back to the spectroscopy. I know some of you guys might still be writing things down. If you want to grab a picture of what's on the board at all, feel free to do that. I'm going to erase what's on the left soon. Do you want to do a vote? Do you want to start with IR or NMR? Raise of hands for IR. And a raise of hands for NMR. Oh, I'm sorry, Pamela. All right. The IRs have it. We'll start with a review of IR. Here's what I forgot to bring you. I'm upset. I forgot to bring you a correlation table. The correlation tables are, the reason I really want to bring it to you guys, the correlation tables are things that I don't know that your organic professors for OChem 1 let you have. So I want you to know them. In fact, I give versions of these correlation tables on my exams. And I say versions because this is more detailed. This has a structural depiction of the bond type that's being analyzed, as well as a written description of the bond type, and then the absorption region and some descriptions. But I do want you guys to know that the descriptions you see on the right are so variable. When certain bonds are present, the shape of other bond peaks change. Depending on the concentration of your sample or the type of IR instrument you use, the shape of the signals change. So these shapes you see on the right should be like a last resort for making sense of what bond causes what signal. I do not give you the visual depiction of the bonds on the exam. I give you the 3 right-hand columns, but I don't give this column on the left. So on your exam, you'll have this correlation table to make sense out of interpreting IR. Although a lot of times, my questions on the exams don't have spectra. It's more of a conceptual question. Which of the molecules in this organic sequence will show a signal between 1775 and 1715? Well, these are organized by absorption range. So finding 1775 and 1715 is actually not hard. And that lines up perfectly with the CO double bond of an ester and a carboxylic acid. But that also has some overlap with the CO double bond of ketones, small overlap of the CO double bond of acid chlorides. So maybe it's the CO double bond of a carboxylic acid. It's definitely a CO double bond. And you'll look at the sequence, this reaction, this multi-step synthesis, and you'll look for the compounds that have CO double bonds. And if more than one of them have CO double bonds, then you could expect to find that signal in the IR spectrum for more than one compound. Okay, I want to back up a little bit and describe how IR works. Remember that mass spec took our sample, ionized it, and then used a magnetic field to pull that ion to a detector. And based on the mass of the ion, it hits the detector at a different spot, telling the detector how heavy that ion was. IR looks at a molecule. It uses light, but it doesn't use visible light. It uses IR light. If we have a compound like acetone and we irradiate it with IR light, the way that an instrument will typically shine a spectrum of light is one wavelength at a time. It uses a device that allows it to kind of scan the spectrum and shoot it. And then its detector looks at whether all of the light it shot out hit it, or what amount of light actually made it through the molecule, and what then tells you how much light was absorbed by the molecule. So if we say that we shoot IR light, and specifically we shoot this high frequency range, we're going to see that the CO double bond doesn't do much. But the CH bonds, they start stretching. And in this high frequency range, that's typically an asymmetric stretch. So this is IR light around 3,000 wave numbers. And it makes the sp3 CH bonds stretch. They absorb that frequency of light and they turn it into this kinetic motion. If I take that same molecule and I irradiate IR light, but I shine it closer to 1750 wave numbers, I make my CO double bond stretch and compress. And carbon dioxide has 2 CO double bonds. Carbon dioxide absorbs really well in this 1700 wave number region, which is why when the ground releases infrared radiation, which is essentially just heat, all of that IR light trying to escape through our atmosphere into space is caught by molecules of carbon dioxide and transformed into kinetic energy. So rather than that energy being lost by the Earth in the form of radiation, it's contained in the atmosphere in the form of kinetic energy, heat. Same thing with methane. Methane absorbs in this high frequency range. So a lot of the infrared light that the Earth's surface emits gets caught in these greenhouse gases. The strongest greenhouse gas on Earth, do you guys know? Water vapor is the strongest greenhouse gas. Water absorbs infrared light better than methane and better than carbon dioxide. But of course, water is part of the water cycle. So there are places where it absorbs heat and then it later rains down, and that heat that it trapped is transferred in other ways. Carbon dioxide and methane have different life cycles. So when they get put into the atmosphere, they keep absorbing heat. They don't stop absorbing heat. Okay, and sorry, I wanted to clarify. This is the CO double bond. I want you to notice that the way I described that CH bond was not just by saying CH absorbs. CH can absorb in a lot of different ways. If you look at the table, the sp2CH of an alkene or an aromatic ring can absorb between 3150 and 3000, just slightly above the region where sp3CH absorbs. And these two regions, very nice. They never overlap. In fact, I will give you spectra. If you look at your IR spectrum right now, you'll see a dotted line at what value? 3000 wave numbers. That dotted line at 3000 wave numbers helps you differentiate absorption from sp2CH from absorption of sp3CH. And the CH of an aldehyde, which I admit is also sp2CH, but I don't really describe it that way. The CH of an aldehyde absorbs differently from all of these other CHs. The CH of an alkyne absorbs differently. So when you identify an absorption peak in an IR spectrum, and I do want to hit on that because I know some of you said you didn't cover spectroscopy. We report on our spectrum wave numbers on the x-axis. That is a unit of frequency reported as inverse centimeters. So it's like taking wavelength and inverting it into frequency. On the y-axis, we look at percent transmittance. So a baseline would have 100% transmittance. Nothing absorbs. But in this example with acetone, we would expect to see these peaks from the CH absorption and then this peak from the CO absorption. sp3CH, CO double bond. Until you get down to 1500 wave numbers. After 1500 wave numbers, a lot of things start to absorb. For instance, CH bonds, which in the high frequency absorb asymmetrically. CH bonds will start absorbing by bending their bonds, and they'll do all of that absorption below 1500 wave numbers. So does NH, so does OH. The CO bonds start to stretch there. The CN bonds start to stretch there. The CC bonds start to stretch there. So there's a lot of random noise down here, a lot of signals, and we call this region the fingerprint. So the other dotted line that you'll see on your IR spectrum anytime I give it to you, and usually when I give it to you, it is in the form of a bonus question. The two dotted lines you'll see 1500 wave numbers to distinguish fingerprint from functional group region, and 3000 wave numbers to distinguish sp2CH from sp3CH. We're looking at a molecule. That is what we're doing. We're using light and we're figuring out what is present. Not everything absorbs in the IR. In fact, the only things that absorb are things that experience a change in dipole if their bond changes, if their bond stretches or bends. But as you guys can see, that's like mostly everything. I have found that alkynes don't show this stretch unless they are asymmetric alkynes, terminal alkynes. One carbon has an H and one carbon has a carbon group. That's the only time you'll see an alkyne absorb. If they both have carbon groups, then there's no change in the dipole moment when it stretches. Excuse me, I don't know, my nose is feeling irritable today. Okay, I want to take some time to take this correlation table and apply it to the spectra that you have in front of you. Let's look at the IR spectrum that's on the left. Actually, maybe one more thing I wanted to point out. Some people will say that your IR spectrum can be broken into regions. The high frequency region is bonds between carbon, oxygen, and nitrogen with hydrogen. High frequency is all bonds to hydrogen. Then there's this small region where we have triple bonds, and then we have this big region where we have double bonds, carbon-oxygen double bonds, carbon-carbon double bonds, nitrogen-oxygen double bonds. A bond I could put in here, but I haven't yet, is the carbon-nitrogen double bond. I'll be honest, I made this correlation table for the use in labs. We don't identify any carbon-nitrogen double bonds in lab, but the carbon-nitrogen double bonds are in here as well. Kind of the only outlier is the NH bending, which is distinct from the NH stretching, shows up in that double bond region. That black line that I have at the bottom is meant to show you the functional groups that absorb only in the fingerprint region. And this is, I want to say this right. These are not the only things that absorb in the fingerprint, but these are things that only absorb in the fingerprint. That means that these are the hardest bonds to identify from an IR spectrum because they will be mixed in with a bunch of other absorptions. It's really hard to find these. I had an OChem 2 lab student, every single IR spectrum of their product, she said, has alkyl halide absorption, despite the fact that none of our products had alkyl halides. Because she saw absorption in the fingerprint region, and she saw that the CX bond absorbs there, so she thought there must have been CX impurity every time. Okay, so with the spectrum on the left, we've got this dotted line at 3,000. I don't see any good evidence for these NH or OH absorptions. These can be medium to strong. The OH is often broad. But there's really nothing up there. You might notice that there's this little dip, just this little tiny peak. These are things that sometimes you just have to wave your hand at and say, I don't think that's a meaningful absorption. That's probably just essentially noise or experimental error. But the first absorption that we see falls just to the right of 3,000 wave numbers, which means it's not going to be an sp2ch. If it was sp2ch, it would have fallen to the left of that dotted line. Because it falls just to the right of that dotted line, this looks like it's sp3ch absorption. The distinction between sp3ch and the CH of an aldehyde is a little challenging. You'll notice that the CH of the aldehyde, though, isn't a range like the sp3ch. It's two values. These are often twin peaks for the aldehyde. It absorbs at 27 and 2800 wave numbers. And if we look, I know it's really challenging to read those little dots, but it does not look like 28 and 27 have those lines. At the very least, we can use more information from NMR later to help us try and correlate back to some of what we see in the IR. So far, sp3ch. As we keep moving right, we see this big signal. Can you guys estimate whereabouts that signal is on the wave numbers? 1750. I'd say closer to like 1710. It's just left of 1700. So I'm going to scroll down because that's the CO double bond region. 1710, maybe it's the CO double bond of an ester or a carboxylic acid. Definitely could be the CO double bond of a ketone or aldehyde. Might not be the CO double bond of an amide, but these ranges are known to shift a little bit depending on how bonds interact with other bonds in a molecule, other groups in a molecule. So it's definitely a CO bond. It's a very strong absorption. But beyond that, I don't really know. As we keep moving right, we get into the fingerprint region. I will never expect you to answer a question about the fingerprint region, but sometimes you can pull out useful information. The signals that I see don't go all the way to the bottom. So I don't think that there is a CO bond, but it's really hard to say. The CO bond would absorb around 13 to 1,000 wave numbers. I mean, there's signals there, but are they strong and sharp? They're sharp for sure, but they're not as strong as the CO double bond. IR is this hand-wavy tool that helps us figure out bonds that are present without much more information. So we're done with that IR. If you labeled sp3ch and CO double bond a lot like what we did here, you've labeled that IR as much as you can with certainty. That's as much as we can be certain about. Do you guys have questions about that IR? Then I want you to take some time to look at the IR on the right. See if you can identify signals. I gave you the harder one. I thought you were saying this was all like one bond. Feel confident about this one, yeah? Maybe? Okay. When you say OH, Jaylee, are you saying OH of, oops, you can't see it. OH of the alcohol or OH of the carboxylic acid? Because they're different. So if you want to label a signal as OH of alcohol, label it as OH ROH or OH alcohol. Because otherwise, the OH of a carboxylic acid absorbs differently. And as much as we should clarify the hybridization of a CH bond that we're labeling, we should clarify the functional group of an OH bond that we're labeling. OH of alcohol shows up broad, but OH of a carboxylic acid shows up very broad. OH of an alcohol has this kind of tight range, but the OH of a carboxylic acid has this massive swath of wave numbers that it absorbs across. That's a challenge at first, 100%. But if you feel like you think it's an OH bond, but you're not sure, then you could put like OH question mark. What type of OH is really causing this? I don't know why I didn't put some of these notes up here. This is the Cliff Notes. 3 things I want you to pay attention to. The bond types. Not all bonds are the same. sp2CH is not the same as sp3CH. So be paying as close of attention as you can to the bond type. Look for corresponding peaks. If you have an aldehyde, then you should have both the CO of an aldehyde, the CO double bond of an aldehyde, and the CH of an aldehyde. Another good one is if you have an amine, you should have 2 peaks from the NH stretch in that high frequency region. You should also expect to see the NH bend in the low frequency region. Anywhere that you see a functional group or a bond type, you should expect that all of their peaks are present. If you think you see one peak from a functional group but you don't see the other, maybe it's not that functional group. Maybe it's not that bond type. And then this variable size, shape, and range. For instance, like different OH groups absorb different. Sometimes signals appear stronger or weaker depending on other signals that are present. And one reminder, that sp2 and sp3, while other absorption ranges might shift, sp2 and sp3 is like a godsend. It is always 3000 that separates it. It never moves. So you'll never have to look at that line and wonder, did it really have sp2 or sp3? I don't know if it just shifted or not. By the way, have I not encouraged you guys to work together enough? You can collaborate. You can talk with each other. And I'm also happy to answer questions. Do you have any questions about that second one to analyze? Justice?
This is what I was asking before class. These twin peaks are like,
I see what you mean.
But they're not at the 2800 and 2700. They're at like 27 and 2600.
Right. So for these, if they shifted to 2810 and 2720, that's pretty close. But to shift to 2700 and 2600, those must just be different. That's a different bond absorbing it. IR will never give you structure, just glimpses at bond types that are present. So what do you guys see in this? Can we point out anything that you feel is obvious? If it's not obvious, what peaks are you skeptical about? Oh, I really. Let's hear obvious ones. Okay, 3000 draws us to our carbon-hydrogen bonds. I've got this nice sharp signal to the right of that. Yeah, it makes sense that that might be my sp3CH. And so many molecules have sp3CH. The odds of a molecule not having sp3CH are kind of low. Not zero, but just low. So yeah, I feel like that's probably sp3CH, sticking right out of the right of 3000. Anything else?
The like 1690.
1690. I agree. Right below 1700.
It's like a CO double bond.
A CO double bond. It agrees with our CO double bond region. Not much else absorbs in that region. 1690 is in range for things like the amide starts absorbing around there, ketones and aldehydes. It feels a little bit out of range for things like esters and carboxylic acids. But remember, depending on the structure, these bonds, especially CO double bonds, if they conjugate, they can shift quite a bit. Actually, a good example of that is the alkene. The alkene absorbs at 1680 to 1600. But the conjugated alkene, which is such a bad descriptor of it, the aromatic ring, fully conjugated, look at how its absorption for the CC double bond shifts to a lower frequency. When alkenes get conjugated, their absorption shifts lower, exemplified by the aromatic ring. If carbonyls are conjugated, their absorption starts to shift lower. Conjugation here meaning a connected series of pi systems. Okay, so a CO double bond. Anything else that you guys see in here? Here's that CO double bond just below 1700. Justice?
Is there an alkene?
Where?
Right below the CO double bond.
This one here?
Yeah.
Yeah, so this one looks like it's 1610 maybe, just a little bit past 16. This one looks like it's right on 16. So maybe an alkene, maybe an aromatic ring. Hard to say. Aromatic rings have some overtones as well, and those typically absorb here, but this is looking a little messy where these overtones show up. So overtones can be useful if they're present, and if they're not present, it doesn't rule it out that there's not an aromatic ring. Okay, anything else? We've got a lot going on the right, a lot more than last time in the fingerprint region. But there is this one signal that is quite distinct from all of the others in the fingerprint, and it shows up around 1270. Maybe that's a CO single bond, hard to say. And the last thing is this like chalice that forms between 3300 and 2500, this cup. That is not typical. You see that there's no cup-like dip for that spectrum we have on the left. That's a very broad absorption. It comes down from baseline, it doesn't get very deep, and it goes back up to baseline over a long time. That looks like the OH of a carboxylic acid. OH of an alcohol, I would expect to see around 34 to 3200, and I don't really see that. But the OH of a carboxylic acid has this nice long shape. And I don't have a good explanation for this, but Justice, those two twin peaks that you were pointing out, that's actually characteristic of the OH of a carboxylic acid. It has all these jagged peaks. It's not one smooth absorption, but it's a broad, jagged absorption. I'm not quite sure why. Well, if we think there's an alkene or an aromatic ring, there's another corresponding peak that should be present. This would be the CC double bond of the aromatic ring. But what other bond type corresponds to the alkene or the aromatic ring? sp2ch. Thank you. The aromatic ring is not just carbon-carbon double bonds. The alkene is not just carbon-carbon double bonds. Those also have carbon-hydrogen bonds that should show up to the left of 3000. So is that an sp2ch? That little shoulder just to the left of 3000? Maybe. If this is a carboxylic acid OH, it's doing a bang-up job on all of our other peaks. It's just eating them all up. So maybe that's an sp2ch. Maybe the sp2ch is hard to identify because it's been swallowed by the OH of a carboxylic acid. It's a hand-wavy science. There's a guy on Reddit. I'm in a lot of the Reddit stuff now. There's a guy on Reddit who calls himself the hand-wavy chemist. And he's got a YouTube channel, and this is exactly why. Because you want to make rules and you want to find these patterns, but there's a lot of stuff that you have to ignore or kind of read into in order to get the information you want. My goal is not for you guys to become masters at this. My goal is for you to glean the most obvious information. Get that foundational skill. Okay, that's IR. Questions? Okay. Let's start into NMR. We've got 20 minutes, so I doubt we'll get through all of NMR, but we can definitely start. When we, I'll elaborate on what NMR is. NMR is nuclear magnetic resonance. It is the same exact technology that you utilize in an MRI. Have you guys ever crawled into an MRI? Or helped somebody crawl into an MRI if you're a nurse? So MRIs obviously don't have the N because nobody wants to climb into a giant tube that clinks really loud when it spins that starts with nuclear. So we don't call MRIs nuclear magnetic resonance imagery, but that's exactly what they are. They look at the nuclei in your molecule. We use light to look at these, to get this as well, but the light that we use is actually radio wave frequency. We will take a sample and we put it into a magnetic field to simplify it. That magnetic field takes the nuclear spin. Nuclear spin is not as simple as electron spin. You guys know electron spin is up and down, right? You've heard that a million times. Nuclear spin can be whole numbers, up or down. It can be integers, or fractions, up or down. It can also be zero. Some nuclei have no nuclear spin. The one that we will study the most is hydrogen NMR, proton NMR. You'll notice that is not its isotope, deuterium. Deuterium does not respond to NMR the same way that H1 does, which makes it very useful. Hydrogen, H1, makes up 99% of all hydrogen atoms. This isotope is the most abundant, so we get really good readings by doing proton NMR. For those of you in lab, I'm hoping that we get to use the NMR tomorrow. I think for those of you in lab tonight, you probably won't use the NMR on methyl orange. Okay, we're looking at proton NMR. We can also look at carbon-13, but carbon-13 makes up 1% of carbon, so it's a lot harder to analyze carbon. It's a lot harder to acquire that data, but it can tell us some useful stuff as well. Some of the cliff notes about NMR. First, we analyze chemical shift. This is one of the most useful pieces of information that we get out of NMR. The unit for chemical shift is delta. Oh no, I think so much of yesterday I was calling delta sigma. I do that too often. Delta or ppm. So you'll notice that is our x-axis. Our x-axis has units of ppm. We call the x-axis delta. We call the x-axis chemical shift. Where a signal shows up is referred to as its chemical shift. So we take these nuclei, we subject them to a magnetic field, and we align all of their nuclear spin, which typically means we're taking them out of their ground state and we're putting them all into a similar state. Then we turn off the magnetic field, and as those nuclei fall back down into their ground state, they emit radio wave radiation. They shine light. just not a visible light. And we pick up that radio wave information and we decode it. A lot of that information, first of all, the signals and their radio waves all overlap. So they have constructive and destructive interferences that creates a really interesting wave pattern. We have to deconstruct that to get down to the principal frequencies that were being combined. As we deconstruct it, we put it into this frequency domain. And the signals appear like this. You'll notice that these signals are generally sharp, but they're not necessarily just one peak. So here's a signal that leaves baseline, comes down into a peak, but before it reaches baseline again, it goes back up into 3 more peaks. And then there's a signal that does leave baseline and comes right back down as just 1 peak. Chemical shift is just showing where that signal is, regardless of how many peaks it has. And we usually center it in the middle of all of those peaks. We can learn something about the functionality from this chemical shift. So back to my next correlation table. Oh, shoot. That's just my IR correlation table. Do you guys know where to find this, by the way, the correlation tables? I've given them to you. I just didn't print them out. Where are they, Justice?
Class resources.
Class resources. Exactly. This is what I wanted. So you can print these off. They're online for you. This is my version of an NMR correlation table. There are many correlation tables out there. This one is mine. Many correlation tables are very detailed. They will tell you the exact chemical shift that you can predict to find a signal in a huge number of different environments. The signal for a CH3 when it's next to a CH2. The location for a signal of a CH3 when it's next to a CH. The location of a CH3 when it's next to an O, when it's next to an N, when it's next to an X. That's too much information. It's really hard to navigate it. It's really hard to give it to you on an exam because it's 5 pages long. So this is the condensed chemical shift correlation table. It is, again, very hand-wavy. And it doesn't actually tell you about every functional group. Alkanes show up on the far right. These are hydrogens where their nuclei are very shielded by electrons. They don't interact with the magnetic field very strongly. They give a very low frequency signal. On the far left are hydrogens adjacent to carbonyls, like the hydrogen of an aldehyde, the hydrogen of a carboxylic acid. Those are hydrogens where electron density is stripped away from them. We say it's de-shielded, which means the magnetic field interacts with the nucleus very strongly, and it gives off a very loud, high-frequency signal. There's some nuance to this as well. Aldehydes and carboxylic acids don't typically make up this whole range. Aldehydes make up more the range of the right, carboxylic acids more on the left, which is why I've given this to you as aldehydes on the right, carboxylic acids on the left, to remind you that in that range, those two signals show up relatively in that order. We can also find some information about aromatic hydrogens. If we see signals in this region, we can feel pretty confident that we've got an aromatic hydrogen. But there is some overlap with hydrogens that are attached to alkenes or vinylic hydrogens. And then there's the functional group adjacent. If you have signal hydrogens that are adjacent to an ether, an alcohol, a carbonyl, halogens, adjacent to alkenes, adjacent to aromatic rings, we would call that allylic or benzylic. Those can all show up in here. And it's really hard to distinguish what shows up where because they all overlap. So I've named this the functional group adjacent range. You can't typically get specific information about a functional group out of this. You just know that the signals are coming from hydrogens next to a functional group. The shielding from the electrons plays another role. If a hydrogen is closer to a hetero atom, it shows up further to the left. If a hydrogen is less close, further from a hetero atom, it shows up further to the right. But these chemical shifts have compounding effects. For instance, if you look at chloromethane, its signal might show up somewhere in the middle here around 3 ppm. But if you look at trichloromethane or chloroform, it's not just that hydrogen is not just adjacent to one functional group. It's not just adjacent to 2 functional groups, but it's adjacent to 3 functional groups. And so its signal shows up at 7.26 ppm. An aromatic hydrogen? No, of course not. Don't be silly. There's nothing aromatic about that. But because it's close to 3 electronegative atoms, it has this chemical shift that just keeps compounding on itself. And it looks like it's in the region of an aromatic hydrogen. So of course it's hand-wavy. We use chloroform, CHCl3, all the time to run NMR signals, to run NMR samples, which means there's often a chloroform solvent peak at 7.26, and it shows up right in the middle of all the aromatic hydrogens, which can be a challenge sometimes if you're interested in knowing about those aromatic hydrogens. So chemical shift is the first, and I would say most important thing about NMR. Spectrum on the left. What can we say with certainty is present or is not present based on chemical shift? So name off some of those. No carboxylic acid. Well, alcohols are actually not on my table. You might have noticed they're not on the correlation table. And that's because alcohols are really strange. Yeah, you know how I said that the closer you are to an electronegative atom, the further left you go? Well, it turns out alcohols are different. The OH and NH groups, those show up over a very broad span. 0.5 to 5 ppm. They don't show up as far left as you'd expect for being directly attached to a hetero atom. Do you guys know why they don't show up that far left? The reason a signal for a hydrogen shows up left is because electrons have been stripped from it. So the electrons would otherwise shield the nucleus from the magnetic field. Those electrons have been stripped. That nucleus is now de-shielded, and its signal shows up further left. And we're saying that these don't de-shield as much as a hydrogen connected to carbons.
Is it because maybe they pull it, force themselves?
The hydrogen, like the atom pulls the hydrogen and the electrons.
I guess, because you're saying like the other ones, the oxygens and the other groups are pulling away from the hydrogen.
Yes.
So maybe on this one, that oxygen itself is pulling the electrons from the other groups towards itself.
But it's definitely still stealing electrons from the H. In order for it to have a signal here, it would need to be shielded, despite being attached to an atom that should de-shield it. How would it get shielded again? It's going to have to receive electron density from something else. Hydrogen bonding. Because OH and NH can hydrogen bond between molecules, the de-shielding that comes from being attached to the heteroatom is counteracted by shielding that comes from hydrogen bonding. They're receiving electron density from other O's and N's. So I don't put them on here, but their range is not as far left as you would expect it to be. Okay, so we don't have carboxylic acid. We don't have aldehydes. What else don't we have? We don't know if we have an alcohol, maybe, although I don't see a 1H, so we'll talk about that later, though. What else don't I have? No aromatic ring. Anything else?
Is it vanillic on there?
Yeah, alkenes. I don't think, this is not the range for alkenes. The fact that my last signal is around 2.5 tells me that I've got functional group adjacent stuff, and I've got a methyl group that is just purely alkane. What about in this one? Anything definitively that I have or don't have? Pamela? Carboxylic acid. How do you know it's not an aldehyde? It's hard to say. The aldehyde would be closer to the 9 to 10, closer to the right of that last region. This is close to 13, so that does look a lot more like a carboxylic acid, but maybe we need to wait to feel definitive, or maybe we look at the IR, and what did we think the IR suggested was present? The OH of a carboxylic acid. So this seems to agree that there is a carboxylic acid. Kwana, you said aromatic ring, because I've got this 6 to 8 region showing signals. Could it be from alkenes that have been conjugated and shifted left? It could, but it's probably an aromatic ring. And then it looks like I've got something, based on our correlation table, does this signal at 2.1, does this look like an alkane signal, or does it look like a functional group adjacent signal? Just barely functional group adjacent. Maybe it's alkane, but we have good reason to suspect that this is adjacent to a functional group. Maybe it's adjacent to the carboxylic acid. Maybe it's adjacent to the aromatic ring, but it's probably adjacent to one or both of them. Okay, the other two features that we will dive into more tomorrow integration, which is how we get all those numbers that you see on the NMR, and splitting pattern, which is the explanation for the peaks that you see. The signals leave baseline. They've got one or multiple peaks before they return to baseline. We say that is the splitting pattern of the signal. Okay, thank you guys. We'll talk about degrees of unsaturation tomorrow. We'll finish up with this spectroscopy problem. We'll solve for those structures. And I think maybe we'll spend some time on resonance. Okay, have a good night. I'll see you guys tomorrow. Is it weird to send you off with a good night at 9:35 a.m.?